This week we're going to talk about thermodynamics, which is a branch of heat but also includes work. So thermodynamics is a branch of physics and chemistry for that matter that deals with the thermal energy, heat, and their relationships to other forms of energy, particularly work. Now, in order to understand or to deal with thermodynamic systems, you have to understand a couple of definitions that I would strongly recommend that you commit to memory and understand very clearly. And the first is the term system. The system is a portion of the universe, a portion of space and matter that you outline and you choose for the purpose of study. In this diagram, the red on the left is the boundary system, and inside the red is the system. And the system can be any shape whatsoever. On the right, it's outlined in the dashed line. So inside the dashed line with the candle and the flame represents the system. Now, everything else, the entire universe, except for the system, represent the surroundings. Now, these may seem like silly definitions, but it's extremely important that you understand this, because we will talk about the effect on the system, and you need to understand what we're talking about. And we'll talk about the effect on surroundings, and again, you need to understand what we're talking about. So, the change of internal energy in a system is equal to the heat added to the system minus the work done by the system. And this is the first law of thermodynamics. This is a practical statement of the conservation of energy, and also states that an object in motion remains in motion unless acted on by an outside force. Now, what you have here is the internal energy of a system, and you act on it by adding heat, or you act on it by having the system do work. In both of those cases, you're expending energy or you're adding energy, and the change in internal energy has to equal to the subtraction of those two things for energy to be conserved. And so that's why this is a practical statement of the first law of thermodynamics. Now, this is what's called a Joule, and it's named after Dr. Joule. It's a Joule experiment, and what he did was to show the relationship between work and heat. And he showed that if you did a certain amount of work on either side here, using the lever to pick up or to lower a object, that you would either generate heat in the middle or you would remove heat. If you did work, if the system does work, then heat has to be removed. If work is added to the system, then heat has to come out. So there's what's known as the mechanical equivalent of work or of heat, and that's the equivalent work that's done that shows the relationship between mechanical work and heat. Now, you have to understand two terms on this slide. First is isothermal, and second is adiabatic. So isothermal means that the system does not change temperature. Adiabatic means the system does not add or subtract heat. They're not the same thing. So if something is adiabatic, no heat is transferred, but the temperature can change. If something is isothermal, the temperature changes, but the temperature does not change, but the heat can either be added or removed. And what you see here is a series of steps in something called the Carnot cycle. And the Carnot cycle is mechanical energy, can produce mechanical energy from thermal energy as heat flows from a high temperature source to a low temperature source. And these are the steps that go on for this to occur. So if you start out with a isothermal expansion, and so heat is added to the cylinder, the temperature remains the same, and it expands, and then no more heat is added, but it continues to expand as the temperature drops from a high temperature TH to a lower temperature TL. Then there's isothermal compression, so there's a compression at the lower temperature with a loss of heat to the outside. And then it continues with no change in heat as you have an increase in temperature from T low to T high. And this is a process where you have heat deposited in a heat sink, and then it continues to go on and on. And an engine a Carnot engine would be a theoretical device that works on the Carnot cycle. Now, if the world were perfect, you could actually do this, and once the engine was started, you would not have to add or subtract any heat to the overall engine. It would lose the same amount of heat as it gains in each of the expansion and compression times, with the temperature remaining the same, and so the heat would go out and then come back in, go out and come back in, and so forth, and you would never have to add any heat. Unfortunately, nothing in real life works that way, and you have to continually add heat to the system because heat is lost to the surroundings and so forth. But this is what's known as a Carnot cycle. Now, the second law of thermodynamics states that natural processes tend to only go in one direction, and that direction is the fact that you always lose energy and have decrease in usable energy with disorder. And that second law of thermodynamics is what prevents a Carnot engine from being absolutely perfect in terms of being used to generate work. In other words, in the process of gaining and losing heat, there's an increase in entropy or increase in disorder that occurs in the surroundings that dissipates some of the heat, so that you have to continually add heat to make up for that. And that increasing disorder is a term known as entropy. And entropy, simple enough, is the idea that things tend to, when left alone, tend to become more and more disordered. So entropy is a measure of the amount of disorder in a system, and all natural systems tend to go to greater and greater entropy. If you put a piece of meat out in the yard, it decomposes. If you put an ice cube on a table at room temperature, it melts, and it ultimately evaporates. And that is the natural process of things. So that means that is why a perpetual motion machine is impossible. Perpetual motion is the ability to self-generate motion once started, and a Carnot engine would do that if not for the second law of thermodynamics and the idea of entropy. Now, in the process of various aspects of matter, they can undergo what's known as changes of state. And what's pictured on the slide here are the three most common states that matter can be seen or found in. There's solids, liquids, and gases. There are a couple other states, but we won't talk about those. And the arrows represent the terms that are defined in the changes of state. So for example, melting is going from a solid to a liquid. Boiling is going from a liquid to a gas. Condensing is going from a gas to a liquid. And freezing is going from a liquid to a solid. So melting is a change of a solid to a liquid, and the temperature at which this occurs is called the melting point. Freezing is changing from a liquid to a solid, and the point at which this occurs is called the freezing point. Evaporation or boiling is a change from a liquid to a gas, and the temperature at which this occurs is the boiling point. And condensation is changing from a gas to a liquid, and the temperature at which this occurs is called the dew point. Now, when you have a pure substance, it has a freezing point. When you add a second molecule or a second substance to that pure substance, it changes the freezing point of that substance. And it does so because the molecules of the second substance get in the way, if you will, of the first substance coming together and forming a solid. And so the general action of a second substance is to lower the freezing point of the first substance, or of the pure substance. And so when you add a solute to the solution, to a pure substance, it lowers the freezing point of that substance. Now, the term latent heat is the amount of energy, heat energy, that has to occur in order for the state to change. In other words, the heat that has to be added or subtracted from a solid for it to become a liquid, or for a liquid for it to become a gas, or for a gas to become a liquid, etc., that's known as the latent heat. And it's called latent heat because it's the addition or subtraction of heat without the changing of temperature. So for the heat, the latent heat of freezing or melting is called the heat of fusion. And this is the amount of heat needed to change a given mass of solid to a liquid or liquid to a solid, depending on whether you're adding heat or taking away heat. And that this occurs without, and this is important, without a change in temperature. So we can use this to work a certain type of problem. Let me show you what I'm talking about. How much heat is needed to convert 50 kilograms of ice at 0 degrees to water at 0 degrees? Okay, and this HF is a shorthand for the latent heat of fusion of water from ice to liquid. So it says how much heat is needed to change 50 kilograms of ice into 50 kilograms of water without a change in temperature. So how would we go about doing that? Well, the heat needed, and we'll call that Q, is going to equal to the mass of the ice times the latent heat of fusion. So in this case, now it's joules per gram, and we've got kilograms here, so we're going to take 500 kilograms times 1,000 grams per kilogram times 334 joules per gram. And then the answer is going to come out in joules. So doing the math here, we get 1.67 times 10 to the 8th joules are required to melt 500 kilograms of ice. And that's a lot of heat that's required to melt that ice. How much heat is needed to change 2,000 grams of silver at 961 degrees into liquid silver? Solid silver into liquid silver. Silver melts at 961 degrees. And the heat of fusion is 109 joules per gram. So we have the heat needed is going to equal to the mass times the heat of fusion, which is going to be 2,000 times 109. And that's going to be 2.18 times 10 to the 5th joules. 2.18 times 10 to the 5th joules.